Professor Gupta?
Dr. Sudipto there.
Yeah, that's why I'm just telling I'm here, sir. At your mercy.
Yeah. After a long time.
Yeah, how are you? You're fine.
So far it's okay.
Everything going well. Okay.
Everything is going well.
Yeah.
So how are you?
It's also so. Everything is going from home. I mean,
Okay.
lecture.
So you are at home only still.
Yeah. All the
Not
classes.
going to the office.
Yeah. Hopefully they will. I mean, they will try to open after October, as the state government is telling, not before that. Let's
Okay.
see.
For us, the university is open.
No, we have to go to university for some administrative jobs and other things. We have to
Okay.
go. But the students' classes are not there. Students are not coming. They are coming
Okay.
only for examination.
So lunch is over?
My batch is over. My lecture is over.
Lunch.
Oh, lunch is also over. Yeah, sure.
Okay. So I also discussing the fundamentals only. So most probably these two will overlap. Let us see.
We are trained in same school.
Same school, yes.
Maybe I should not disturb anymore because this is we are personally.
No problem. We'll continue.
Please concentrate. Thank you.
Sir, can we start the session, sir?
Yeah, please.
Yes, sir. Thank you.
I welcome back all the dignitaries. Now, I request Assistant Professor Mr. S.V. Charnath from Department of Mechanical Engineering, Kingston Engineering College, to give a brief introduction of keynote speaker, Dr. AVSS Kumarasamy Gupta.
Good afternoon, everyone. I welcome Dr. AVSS Kumaraswamy Gupta, Professor and Head Mechanical Engineering, JNTU Hyderabad. Dr. Gupta has completed his bachelor degree in Mechanical Engineering from JNTU College of Engineering, Anantapur in 1993. Master's degree in Mechanical Engineering from Regional Engineering College, Warangal, and doctoral degree from Indian Institute of Technology, Kharagpur in 1999. After obtaining the doctorate degree, he joined as Assistant Manager R&D Division, Tata Steel, Jamshedpur from 1999 to 2001 and came for teaching in 2001. He joined as assistant professor in JNTU Hyderabad College of Engineering in 2001 and promoted as associate professor in 2003 and professor as a professor in 2011. So he did his PhD research work at University of New Brunswick, Canada in the year 2004. He has done several administrative responsibilities at JNTU as a head of department, controller of examination, and TN QIP, that is Technical Education Quality Improvement Program Coordinator, Special Officer, Nodal Center in charge, Officer in charge of Examination, Hostel Manager for boys hostel, and etc. So he has visited different countries to present papers and post research work, namely USA, Canada, Singapore, Malaysia, Hong Kong, Thailand, Indonesia, etc. To his credit, he has published more than 175 papers in international and national journal and conferences and already guided 23 doctoral students. 8 more students are pursuing their doctoral work under his supervision. In addition, he has guided 75 post-graduation projects and 65 undergraduation projects. He is a member of NAC and AACT peer review committee member. Has received a second best paper award from Tata Search Journal in 2001 and certificate of merit for the paper published the Institution of Engineers in 2000. So I welcome you again, sir. I welcome you to this FDP. It is very honorable for us to have a word with you. I'd like to hand over this virtual dais to Dr. Gupta to share his valuable knowledge. Thank you, sir. Thank you for coming.
So, good afternoon, one and all. Respected dignitaries who are organizing this 5-day faculty development program, and my dear friend Professor Sudipta De from Jadavpur University, who was co-research scholar at IIT Kharagpur under Professor P.K. Nath, then other participants and students. I'm happy to be associated with this particular faculty development program, which is being organized under ATAL scheme by Kingston Engineering College, Vellore. This particular entire program is basically meant for Exergy and Exergo economic analysis of power generation systems. As you are aware, many researchers and many faculty members are already working in the area of Exergy analysis and how it can be practically implemented for design and optimization of thermal equipment and thermal systems. As a part of this particular workshop, I have been given an opportunity to have the interactions with you related to this topic and also to give the fundamental concepts which one needs to understand to cope up this particular Exergy analysis. Most of the people feel that the Exergy analysis or Exergy term is relatively new and it is different term. In reality, it is not much different from your energy and it is connected to your energy, and its analysis is also connected to your energy analysis and where it has been started and how this Exergy analysis has been initiated, why Exergy analysis has to be done based on thermodynamic analysis. I would like to discuss maybe for next 1 hour 15 minutes or 1.5 hours. Okay, so with this introduction, I'll try to share my PPT. Is the screen visible to all of you?
Yes, sir. Yes.
Yes.
Kindly proceed, sir.
Yeah.
Yes, sir.
Just a minute. Let me. So the fundamentals of Exergy and its role to thermal design and optimization. This is the topic which has been given by the organizers, and I tried my level best to modify this particular lecture to suit your requirements and to continue for further lectures given by other speakers from day 2 onwards, because most of the teachers from the second day onwards, they might be giving completely inputs related to how it has to be applied for different practical applications, either power cycles, refrigeration cycles, thermodynamic systems, equipment, and so on. For all the components, the second law analysis has to be incorporated so that optimization and design will be better. So the contents of the present lecture will go in this way. Initially, I will discuss about what is thermodynamic model. Anyway, all the teachers, all the speakers, whoever will be discussing in the next 5 days for you, everybody will be discussing about this thermodynamic model only. I'll try to give where this Exergy analysis is fit into and how it has to be taken into account for doing the analysis. Then I'll start with the limitations of first law. Before going to the second law, what was the limitations and how the Exergy has come into the existence for understanding. Then what is the quality of energy and what is the need of understanding this quality. Then how do we quantify the quality of energy? Once after knowing the quality of energy or qualitative difference among the energy resources, it may be our responsibility to make it the quantification of the quality of energy. That quantification itself is being called as exergy or available energy. So when you try to quantify the qualitative energy, that quantification has been considered as your exergy or available energy. So far in our curriculum in the second year of undergraduate program in any of the universities, most of the universities are having in second year, and some of the universities are having in first year. Immediately after the second law, they discuss about available energy and what is its implications and why should we study it, and what are the other parameters which needs to understand, how to calculate the available energy, unavailable energy, energy reversibility, and so on, and how it is made applicable for the power systems. I'll be discussing up to that. Then after people will discuss about your practical applications. So in this way, at last I will try to discuss just briefly about clash statement, because most of the second law has been discussed, basically dealt with the Kelvin Planck statement, and finally I will try to discuss the significance of clash statement maybe in the last 1 or 2 slides, right? Now we come to the thermodynamic analysis or thermodynamic model of power cycles. Whenever you want to analyze, whenever you want to design, or whenever you want to study about any thermal systems, either you take gas turbine power plants, steam turbine power plants, internal combustion engines, and other power generating systems. For the time being, let us not discuss about power consuming devices, and let us focus majorly on power generating devices. All these power generating devices works based on power cycles that you might be knowing. So that means the low grade energy, that is heat energy, is being converted into mechanical work in all power cycles. To give the examples of power cycles, that is Otto cycle, diesel cycle, dual cycle for internal combustion engines, Brayton cycle, Atkinson cycle, and other cycles for the gas turbine cycles, Rankine cycle will be for the steam cycles, and so on. There are many power generating cycles, and there are advanced power cycles also, like combined cycle, cogeneration systems, and Colina cycle, Bresson cycle, and so on. So many cycles are being invented by different people for making power generation from the low grade energy or heat. So for doing the mathematical model, because it is having a lot of potential, one has to do, and you might have studied completely this about these power cycles in your undergraduate program as well as post-graduation program. Up to that, we did basically the energy balance. Here I have given the energy balance. For doing that energy balance, whenever you make your power cycle model for energy conversion from heat into work, after making the model, rather after keeping all your components required, the cycle will be drawn. Based on that cycle, you need to make the mass balance. You already know that for flow process, the conservation of mass has to be taken into account. You need to make the mass balance for the entire cycle. In each component, some quantity of mass is entering, some quantity of mass is leaving, and some quantity of energy entering and some quantity of energy leaving, and so on. When we say the thermodynamic model, you need to do majorly the mass balance and energy balance if you feel up to first law of thermodynamics. If you want to extend the first law of thermodynamics for the model to second law, if you want to make it second law analysis, additionally you need to do Exergy balance. Why I am specifically discussing about this thermodynamic model to all the people, the main idea is a lot of potential, lot of research gap is available for the new research scholars to take up these activities and to do the Exergy analysis for all the existing power plants and equipment, so that optimization can be done and the design of systems can be made. So to make all these three, if I say the first law analysis, mass balance and energy balance are sufficient. if you wish to do the second law analysis also for the power cycles, you have to add this Exergy balance. All three put together will give better design optimization for the given thermal systems. To do all these three, you require gas properties and steam properties. This is another major important input parameters for the analysis of thermal systems, because the gas properties, why only these two are important? Because gas properties means it taking into the account of air as well as gases. These gases properties are sufficient for doing your internal combustion engines cycles and gas turbine cycles, whereas for other cycles the steam properties are required. If you go beyond these two, and if you want to analyze refrigeration cycles and other cycles, you need to have your own properties of that particular working substance. So whatever the working substance you are choosing, for example, if you say apart from these two, if you say the Kalina cycle, immediately ammonia water mixer properties are required. So when you say the ammonia mixer properties, again you need to use some of the real gas equations or other equation of state for our practical applications, and you need to develop or you need to generate your own programming code for getting thermodynamic properties. Ultimately, I need to say, whenever you want to make a thermodynamic model for the system, you need to do these three balances: mass balance, energy balance, and Exergy balance. The analysis will be done in all the three interlinked for all the components which are existing in the cycle. To make all these three, you require support, that is gas properties and steam properties. If these two are not sufficient, it depends on your working medium. If working medium is something else, you need to generate your own properties and you do the analysis. Then you can do your parametric optimization either for combined cycle or different triple power cycle, tri-generation system, or any new advanced topics of this gasification process or clean coal technologies. Lot of thermodynamic cycles are nowadays available and which are to be optimized and also made practically implementable for future power generation industry. So with this intention, I'll try to start my lecture. So let me give briefly introduction before going to the Exergy. I don't want to discuss completely the basics of thermodynamics, which whoever is the participants, majority of the participants already might be knowing about the basics of thermodynamics and also the first law. And I will start my lecture from the basis of the first law and what are the limitations which does it have and how to overcome these limitations and how the second law can be applicable and what is its importance. Finally, I would like to touch upon entropy generation and how entropy generation will be useful for making your second law analysis, and so on. I will try to extend for the today's lecture. Let me take the introduction. Just I will give the statement of first law of thermodynamics, which you might have already studied. The first law of thermodynamics states that energy neither be created nor be destroyed, but it can be transformed from one form to other form. So because energy transformation is existing, because you need to make energy transformation according to our requirements of our practical applications, this thermal engineering has come into the existence. You need to study about all thermal equipment. If energy conversion is not necessary, you don't require this thermal equipment. So since energy conversion is required, when you try to convert the energy from one form to other form, the first class plays a vital role. The total energy that is existing on the universe is constant. This is the point to be remembered. Whatever the thermal energy or total energy which is existing on the universe is constant. You cannot create the energy and you cannot destroy the energy. Only thing is the energy depends on its existing form. We try to transform that energy from one form to other form, depends on our requirement. For example, if you take your air conditioning system, what we will do, we will try to take the electrical energy or solar and other energies as input, and it will be trying to convert into cooling effect or heating effect, depends on our requirement. Similar way, whenever you try to transform the energy from one form to other form, the first law will be playing the role. There is another way of giving the statement of first law of thermodynamics. The heat transfer and work transfer are mutually transferable. Really practically transformable are not being discussed. Anyway, I'll try to discuss based on the first law of thermodynamics has been given. These are the major important limitations which were not addressed when the first law is being evolved. So the first limitation, the quality of energy has not been taken into account. Always the first law deals with, if suppose if you have some 1000 kilojoules of energy with you and it can be transformed into the useful form and it can be converted into the useful form. Really, does it have the quality or not? Does it have the quality or not has not been taken into account. The feasibility of the process has not been discussed. The process can occur or not. When this entropy concept has come into the existence, if you know the total entropy generation, based on the entropy generation, we will come to know that practically the process has been feasible or not. Sometimes people say that if this much quantity of energy is available, we can transform it into some other form according to our requirement, and practical, when it is coming to the practical, it cannot be converted because of it is not possible or it is not feasible. I would like to add one more point here. The most of the energy, maybe some 60 to 70% of energy which is existing in the environment or atmosphere, it is absolutely doesn't have any quality. Already we start foregoing the quality of energy and making it as a non-qualitative energy. So all these are being taken into account when you come to the second law of thermodynamics. The third point is the direction of energy flow. The direction of energy flow is not being taken into account. These three are major limitations which were not addressed while discussing about the first law of thermodynamics. Don't mistaken me. I'm not saying that the first law is wrong. First law is absolutely correct and absolutely practically valued and practically implementable. Only thing is it has certain limitations. Those limitations are to be overcome by the second law of thermodynamics. And you try to design the components based on the second law of thermodynamics. It can be better optimized. That is the idea of the second law of thermodynamics. Now, let us start discussing about the first limitation. Quality of energy has not been taken into account. So let us discuss for a few moments about quality of energy. When I say the quality of energy is the potential of that energy to produce maximum useful work in a given environment. Here, when you try to understand or when you try to know the quality of energy, environment will play the role. This is the point to be noted. So people, while discussing about the second law, we dealt with the P0 and T0, that is the atmospheric pressure and atmospheric temperature, which are being considered as a dead state, which will have a lot of influence to know its quality. Right? The quality is used as the sense of degree of usefulness to the society. How this energy is useful to the society will be called as the quality of energy. If the quality of energy is existing in the energy, definitely it will be having the transformation possibility. If it doesn't have the quality, certainly it cannot be used for transformation. That is the quality of energy. To give an example, the quality of same quantity of energy at 1000 Kelvin and 500 Kelvin are different. So I am trying to take two different energy sources. One energy source is at 1000 Kelvin and other energy source is at 500 Kelvin. Even if you take the same quantity of energy, the qualitatively its quality is different. And how it is different? The energy existing in 1000 Kelvin is more qualitative than the energy existing at 500 Kelvin. Absolutely, it is known fact only to all thermal engineers. We pretty well know that at 1000 Kelvin will have the higher quality. At 500 Kelvin, it will be its quality is less than that 1000 Kelvin. Obviously, if the energy is existing at higher temperature, will have the higher quality. At higher pressures, will have the higher quality. But when I come to the first law of thermodynamics, if you take some quantity of energy, it doesn't bother it is having the quality or not. Now let me check the quality of energy. So just we try to conduct a small test for the energy sources from where you are getting that energy, and we will try to see that how much does it have the capability of transformation for making the testing. I am connecting the energy sources to a reversible heat engine. Why I am connecting it to a reversible heat engine? Basically all the reversible heat engines are having the maximum efficiency, and also all the reversible heat engines have the equal efficiency for the given temperature limits. So that is the statement given by the Carnot, and based on that, the reversible heat engines will definitely give the better or maximum work output. So I have taken the energy from two different sources. For making comparison, I have drawn the third energy source, which may be at 300 Kelvin. So here, if you see carefully, I have tapped 1000 kilojoules of energy from all the three different energy sources. Energy sources are different, reversible heat engines, and which are connected to a common sink of same temperature, because the atmospheric temperature or other sink conditions, I am assuming it as same, except the source. Except the source, all the other things are same for testing the quality of energy. From the first energy source, I think you know the equation for calculation of reversible work for any of reversible heat engine, which is equal to Q1 into 1 minus T2 by T1. This is a standard equation which is known to all of you, where T2 is the sink temperature and T1 is the Q1 is the heat that is tapped from the source. Now, if you give inputs to this equation from the first energy source, if you tap 1000 kilojoules of energy, you are getting 700 kilojoules of work. From the second, I am tapping same 1000 kilojoules of energy. Quantitatively, I am taking the same quantity of energy and I am connecting it to a reversible heat engine of equal nature of previous one, and I am getting only 400 kilojoules. What happened to this 300 kilojoules? Who has taken this 300 kilojoules of energy? Rather, we can say that this 300 kilojoules of energy has been wasted. Though the engine is qualitative and other conditions are qualitative, because of energy of existing condition, we are unable to make the transformation. We are unable to make the transformations of first energy. The reason is the qualitatively it is different. In a class of 60 students, each student will get different marks. The teacher is same, class is same, question paper is same, syllabus is same, textbooks are same, and everything is same. But when it is coming to the declaration of the results, you will be getting the different marks, because there is a qualitative difference in the source which is existing. That quality has not been taken into account while discussing about the first law of thermodynamics. Always it says that if you tap 1000 kilojoules of energy from somewhere, and if you connect it to a engine, you may be getting this much quantity of work. Practically, are you getting or not, and really it is having the potential or not, will be dealt by this quality of energy. To make further comparison, I have connected from the energy source of 300 Kelvin, and I have tapped 1000 kilojoules of energy connected to a same engine, and I am getting only 0 kilojoules. What does it mean? Is energy, we are not destroying. 1000 kilojoules of energy we are taking, but when we come to the transformation, we are getting only 0 kilojoules. Because why the energy output from this particular energy source is equal to 0? Because it doesn't have the quality. So once it doesn't have the quality, you have to think at what conditions it doesn't have quality, at what conditions does it have the quality, and how to make use of that energy qualitatively. That will be taken care by so-called your second law of thermodynamics, right? So if you make the comparison of all the three energy sources, you are tapping 1000 kilojoules of energy from three different sources at higher temperatures, you will have the better work output, and the remaining two will be having the second and third and so on. And when it is coming to the same temperature of source and sink, the qualitatively its value is 0. It means whatever the energy that is existing exactly at sink pressure and temperature, it doesn't have any potential for transformation. Once it is not having any transformation, means that energy has become dead. Thermal death is achieved. So you have to think, or you have to protect the quality of energy qualitatively, and you try to convert into some other form before losing its quality. The second law basically is dealt with when the energy is having a certain quality. If you leave it as such, it starts losing its quality on its own. You need not do anything. you have the hot water in a bucket and leave it as such. What will happen that hot water after a certain time, since the surrounding temperature is lower than the water temperature, slowly it starts losing its heat. As long as it is hot water, it is having the qualitative energy. Once it reaches to the atmospheric temperature, its quality is becoming zero, like your third system, which is shown on the figure. Once its quality has come down, then absolutely it becomes useless. So as the energy slowly losing its quality, that's why the second law of thermodynamics is being also named as law of degradation of energy. The quality of energy starts degrading with the time as well as temperature. So once it is degrading, it is our responsibility to make it useful while degrading. It starts degrading, there is no other go. Generally in the class also I used to give an example to the student. When student coming into the campus, he will be having the fresh mind with a lot of enthu after intermediate, after successful in the competitive examination, with so much of spirit, he will enter into the campus of more qualitatively, but the system and environment will change him. Slowly it starts degrading its quality. That means he starts making friendship, this, that and all starts degrading. So while that degradation, you have to be careful for making it into transformation. Degradation is a mandatory. Degradation will happen for any of the qualitative energy source, and you have to make it to useful form before it is being degraded. For the same quantity of energy, why difference in work output of the same engine? That is only the difference, that is the quality. Now, the quality is a relative term. When you say the quality of energy, one energy source is having better quality, one energy source is having lesser quality and intermediate quality and so on. For engineers, certainly the qualitative difference may not be sufficient for designing of the equipment. So it is essential to quantify that quality of energy. Whatever the quality which you are expecting from any energy source, if you are able to quantify its quality, at the initial starting itself, we can say that its quality is 0. Initially, you can say that its quality is this much. To check that quality, the state level entrance examinations are conducting, and if you feel that they are having the quality to study engineering, then only they are being given the admission. If quality is not there, definitely they don't give. So here also, you need to quantify the quality of energy based on its existing conditions. The quality of energy can be quantified based on second law of thermodynamics, in which the surrounding conditions will play the role. The environment and surrounding condition will play the role, and the second law of thermodynamics will be coming into the existence. Right? Now, first I will try to discuss briefly about second law, then how it can be linked to your quality. The second law of thermodynamics, basically considering the following points, it recognizes the quality of energy. When you discuss about second law, it is taking into the account of quality of energy. Even the same quantity of heat at different temperatures will have different qualities that I already. Gradation between types of energies. It will be helping us to grade based on its direction of energy transfer and conversion capacity. It can be, energies can be graded. It is also called as law of degradation of energy, since the practical processes result in degradation of energy. Slowly, as the processes are going on, the quality of energy will be degraded. It also introduces the concept of entropy. The entropy has been brought from the second law. However, it was being discussed before first law, but they do not know that that was entropy. When you come to the first law of thermodynamics, we know that energy transformations are of two forms from thermodynamic point of view: work transfer and heat transfer. For drawing on the PV diagram, for work transfer, integral PdV will be work transfer, and for getting the heat transfer, integral T into certain dx. X has been given unknown parameter as long as we discussed about first law of thermodynamics. But after the second law of thermodynamics, people got the importance of second law and entropy, and that has got its own prominence, and it has been introduced into our content. Now we'll say the second law of thermodynamics. What does it say? It has been given in two statements. One is Kelvin-Planck statement, other one is Clausius statement. When you say the Kelvin-Planck statement, it is impossible to construct a heat engine operating in the cycle to produce shaft work by exchanging the heat with the single thermal reservoir. So we may not be in a position to construct a heat engine which can generate the work, because heat engines are being generally used for converting into heat energy into mechanical work. While converting with single reservoir, it is impossible. You have to have one reservoir for heat tapping and one reservoir for heat rejection. In other way, it can be said that it is impossible to operate a heat engine which can transform the heat into shaft work without any heat rejection. Without any heat rejection, it is impossible to transform the heat into work, and such fictitious machine cannot be made. Right? So here I have given the same Kelvin Planck statement in the heat engine form. Here you can see the reversible heat engine. It is having the better efficiency, and source temperature is being taken as T or any other temperature. And I try to tap 1000 kilojoules of energy and connect it to a reversible heat engine. And if you are able to convert this 1000 kilojoules into 1000 kilojoules of work, complete conversion, 1000 kilojoules of energy into 1000 kilojoules of work, in this case, the quantity of heat rejection is 0. The quantity of heat rejection is 0, right? That means this is Kelvin Planck statement which is impossible to construct. The violation of Kelvin Planck statement will become PMM2, that is the perpetual motion of machine kind 2. That means without heat rejection, it is impossible to construct a heat engine which can transform the heat energy into mechanical work 100%, which is practically impossible. Now we may be getting the doubt, what is the link between this quality of energy and second law of thermodynamics or Kelvin Planck statement? How this Kelvin Planck statement can take into the account of your quality of energy? Just I will try to go back to the engines which have been shown here earlier. So far, while discussing about this, I discussed only about the source. 1000 Kelvin, 500 Kelvin and 300 Kelvin. The 1000 kilojoules of energy has been tapped from these different sources, and I am trying to convert into the mechanical work. We are getting 700 and 400 and 0 Kelvin. The major important part to be noted here is the quantity of heat rejection is 300 kilojoules in the first case. The quantity of heat rejection is 600 kilojoules in the second case. The quantity of heat rejection is 1000 kilojoules in the third case. In other words, I can say that the quality of energy will depend on the quantity of heat rejection during transformation. If the quantity of heat rejection is more, the quality is less. If the quantity of heat rejection is less, the quality will be more. So the quantity of heat rejection will play the vital role in order to understand the quality of energy and also the quantification of quality of energy, right? So the quantity of heat that is rejected in the three cases have been shown. It is having the increasing order. Since the first energy is highly qualitative, the quantity of heat rejection is less. The second one is medium, and the third one is maximum, which is absolutely possible. And if I try to club this, here the quantity of heat rejection is 0, right? It understands whenever you want to make its transformation, if the quantity of heat rejection is 0, which is impossible, if the quantity of heat rejection is maximum, the quality of 0, all other energy qualities will be lying between these two. I repeat, if the source temperature and sink temperature are of at same temperature, the quantity of heat rejection is maximum. If the sink is not existing according to our Kelvin Planck statement, the quantity of heat rejection is 0, which is impossible. And if energy is losing its complete quality and the transformation is absolutely 0, under these circumstances, the quantity of qualitative energy is 0. So the energies based on its quality will be lying between these two. All these will be depending on the quantity of heat rejection. The quality of energy will depend on the quantity of heat rejection. If the quantity of heat rejection is more, the quality will be less. Now the question arises, to make the quantification of quality of energy, they try to define a term called available energy. The available energy or Exergy means the quantity of qualitative energy. Any energy which is existing at certain temperature and pressure will have its own quality, and you do not bother much about quantity, right? So now, to make you to know the quality of energy, let us take 1000 kilojoules of energy at 1000 Kelvin. That means I have some energy source, maybe from boiler or combustion chamber in the gas turbines or cylinders in the internal combustion engine. I have the energy source for our heat energy, assuming that the heat energy is existing at 1000 Kelvin, and I have enormous quantity, may not be 1000, or you may be having certain quantity of energy we are tapping. And I would like to know what is its quantity of qualitative energy. The quantity of qualitative energy is, if you connect it to a reversible heat engine, you may be getting the energy conversion. Since it is having the quality existing, to know its quantification in prior, the quantity of qualitative energy or exergy as an imaginary term. Like your energy, we'll try to know what is its exergy, what is its qualitative energy. That has to be quantified with reference to certain condition. That reference condition will be taken as the atmospheric condition or surrounding condition. In this way, the surrounding condition has been brought into the analysis for making the calculations. So to know its quality, if I say the quality means whatever the maximum potential does it have. The quantity of qualitative energy is being defined as the maximum potential does any energy is having. That we call it as, not only for energy, this potential has to be taken into account for human beings, for all other. Every system or every person or every creature will have its own maximum capability. That we call it as exergy. In other words, I can say that for the students and people, the IQ level, the students say that this person is having this much IQ level, means that is its qualitative energy. Or quantity of qualitative energy, I can say that is IQ level. Right? So how do you get its maximum potential for any of the given energy source? To get its maximum potential, you connect it to a reversible heat engine. Why I am connecting it to a reversible heat engine? Already I have mentioned in the earlier slides. It gives us the maximum potential or maximum efficiency under the given conditions. So it is the capable for giving maximum. And if you start reducing the sink temperature, if you start changing your sink temperature, you may be getting the variation in your work output. I want to know what is the maximum capability of my energy source of 1000 Kelvin of 1000 kilojoules. To know its quality, I am trying to conduct a small test with the reversible heat engine by changing its sink temperature. First, I have conducted the experiment with 300 Kelvin sink temperature. I am able to get 700 kilojoules. Can I say that it is its maximum capability? I cannot, because we have to check in other way that it will be having the better possible base. If I reduce the sink temperature to 200 Kelvin, my heat rejection is 200 kilojoules. I am able to get 800 kilojoules of work. Can I say it's maximum work output? I cannot say, because the problem is making the 200 Kelvin of sink temperature is a tough task. Sink temperature of atmospheric condition is absolutely possible. If you want to maintain the sink temperature below the surrounding temperature, certainly you need to expedite some quantity of work to maintain the sink temperature below the surrounding temperature, which will be again a loss, right? So if you reduce the sink temperature to still further, if you make the sink temperature to 0 Kelvin, you will get your 1000 kilojoules, which is your violation of second law, or your PMM2. That means if you make 100% heat conversion, heat energy into mechanical work, 1000 kilojoules into 1000 kilojoules, under these circumstances, the quantity of heat rejection is 0. To make the quantity of heat rejection is 0, your sink temperature must be 0 Kelvin. It is absolutely impossible. Hence, the second law cannot be practically, that fictitious mission cannot be made practically implementable. Now the question arises, how long the sink temperature can be reduced. If you reduce the sink temperature, we know pretty well that you will be getting the better performance or better energy conversion. But how long the sink temperature can be reduced? If you go on reducing the sink temperature, work output will be improved, the quantity of heat rejection will be reduced. However, it cannot go below certain value. As the sink temperature reduces, the work produced will increase. The maximum work would be if the sink temperature is T0. You cannot reduce the sink temperature further below T. Practically, you can do it, but for theoretically, for better output, you cannot maintain the sink temperature below the surrounding temperature because of its practical difficulties. To maintain that, you need to expedite some quantity of work. Then only the sink temperature can be maintained below the surrounding temperature. So whatever the work output which you will be getting, if the engine is connected to a reversible heat engine and maintaining the sink temperature as the surrounding temperature, whatever the work output you are getting, that we call it as the maximum work output or the quantity of qualitative energy from the given energy source. So that the maximum work would be if the sink temperature is T0, which is 25 degrees centigrade, can be taken as a standard atmospheric temperature, which is equal to 298 Kelvin. If you substitute, W max is equal to 702 kilojoules. I repeat here, if you have the 1000 kilojoules of energy with you at 1000 Kelvin, and the quantity of qualitative energy possible for conversion is 702 kilojoules, don't feel that you have 1000 kilojoules. According to the first law, it says that you are having the 1000 kilojoules of energy is available for you for conversion, but when it's coming to the practically, available energy is only 702. 702 only will have the possible conversion. You may be getting that much quantity or not, we'll come to know in the latter days. But when it is coming to the practical conditions, by taking into the account of quality of energy, surrounding condition, and second law of thermodynamics, we are able to know that maximum work output from the given energy source with respect to the surrounding temperature of 298 Kelvin is 702 kilojoules. 702 kilojoules is being called as exergy of that energy. If suppose your source temperature is 298, even if you have 1000 kilojoules of energy, its qualitative energy is 0. It means the quality of energy at T0 is always 0. The quality of energy at T0 is 0. Now I would like to define a term called available energy or exergy. The quantity of qualitative energy which is being named as available energy or exergy. It indicates any energy will have the two components. Any energy will have two components. One is available energy, other one is unavailable energy. Available energy we call it as exergy, unavailable energy we call it as energy. The exergy or availability of a given system is defined as the maximum work that is obtainable. I try to underline here is obtainable because it is an imaginary term which will be helping us to know what could be the maximum work. Right? Practically, you do not achieve. When do you achieve this? If your engine is a reversible heat engine and sink temperature is T0 under ideal conditions, then only the transformation is possible. Otherwise, we can feel that that much quantity of energy, qualitative energy is available. How much is transformed? That anyway will come to the actual efficiencies which you are getting from our practical conditions. So the maximum work that is obtainable in a process in which the system comes to equilibrium with its surroundings or dead state. So P0 and T0 are being taken as dead state. The quantity of qualitative energy at that particular point is being considered as dead state. If energy is existing away from this point and also below that point, it will be having its own quality. Why the P0 and T0 only are being taken into considered as your dead state? The reason is, okay, so the exergy is thus a composite property, not like your energy. Here it is a composite property depending on the system, whatever the capabilities which the system is having, and also the surroundings. Both combinedly will be taken to make the calculations for your available energy. So available energy or exergy can be given based on this previous relation here. It is a reversible heat engine. Whatever the maximum work output which you are getting is equal to 1 minus the sink temperature I are maintaining as T0. 1 minus T0 by T1 into Q1 will be called as quantity of qualitative energy or exergy. This is the major point to be noted. Whenever we have the Q1 quantity of energy, don't feel that that energy is having the potential for conformation or transformation. But when it's coming to the practicality, this will be composite property. If T1 is equal to T0, let us say that T1 is equal, that is the source temperature is equal to the sink temperature. Even though if we have enormous quantity of Q1, the exergy value is 0. You remember the quantity of qualitative energy is 0 if it is existing at T0. So 1 minus T0 by T1 is the efficiency of a reversible heat engine working between the temperature limits of T1 and T0. Why it is called the dead state, that I'll try to touch upon. So this is the PV diagram and TS diagram, and exactly at that point we call it as dead state. This is your constant T0 line, isothermal line, and this is constant pressure P0 line. If energy is existing, let us say at state point 1, with respect to this P0, this much of exergy is available. It is having the potential. Similarly, if energy is existing at this point, we'll also have the exergy. Exactly at this point, it doesn't have any value. That is the beauty of the exergy. Its quality is absolutely 0. The quality of energy is 0 at the dead state. The energy is qualitative above and below the dead state. If all the thermal energy reaches to dead state, means it is thermal death achieved. So the thermal death is achieved if all the quantity of energy reaches to the, that means, to make you understand, okay, small example, if you take a metal block which is existing at 500 Kelvin, let us say, our atmospheric temperature is 298 and the black temperature is 500 Kelvin. At 500 Kelvin, certainly it will have the exergy between 500 to 298. If you leave it as such, what will happen to the quality of that energy? Starts slowly degrading and losing its energy to the atmosphere, because atmosphere is having interaction with that black and heat will be transferred and it will be losing its energy and it reaches to the dead state. Even if you, after reaching to the dead state, if you leave it as such, its temperature will not be reduced further. The reason is already it has been in equilibrium with the atmospheric condition, its temperature will not be further damaged. Once it reaches to the T0, means its damage has been happened. Even for the student also, I used to give the example for the student. He starts losing its quality by having the friends this and all. Finally, he doesn't read. Once it gets the 0 marks or less than threshold marks, immediately I can say that his quality is 0 and he cannot become transformable to engineer. Once it reaches to the dead state, further damage cannot be occurred. Similarly, if the energy is existing at the temperature below the surrounding temperature, once the energy is existing below the surrounding temperature, automatically it starts increasing its temperature because the surrounding temperature is higher. Finally, it reaches to the D0. Finally, we can say that the P0 and T0 is called as dead state. All the second law of thermodynamic properties are all these composite properties are being calculated based on the environmental condition. So environmental condition will play the vital role to know the quantity of qualitative energy. Hence, the Western countries, they are having the lower value of surrounding temperature. Hence, the quality of energy is better for them compared with Indian conditions. Even in India also, summer, the surrounding temperature is 40 to 45 degrees centigrade. It is higher. So whatever the same quantity of qualitative energy which is available with us will have the lower quality in summer compared with the winter. Same work output you may not get from thermal power plants in summer than winter. In that way, the quality of energy will have a lot of influence by the surrounding temperature. Once after understanding the available energy or exergy, in the given energy component, you have the available energy or quantity of qualitative energy. Now it is our responsibility to know the unavailable energy or energy. I already said, if there is no heat rejection, there is no unavailable energy, it is impossible, which I call it as PMM2. There is certain quantity of heat rejection, which we call it as unavailable energy or energy. Some heat must be rejected. The minimum amount of heat that must be rejected, not rejectable. I am saying that is must be rejected while transforming the heat into work is being named as unavailable energy or energy. So energy contains two components, that is exergy and energy. So when I say the first law of thermodynamics, we are always discussing about only energy. When it's coming to the second law of thermodynamics, along with the mass transfer, you need to consider only the exergy. We do not bother much about energy. Energy is anyway you have to forego. Without foregoing, that much transformation cannot occur, and we need not bother about much while doing analysis of this energy, and only the major part or major role will be based on exergy, right? So whenever we say the energy, we have the two components, one is exergy and other one is energy. Once after understanding this available energy, okay, anyway, I'll come back again after the irreversibility, right? Now I need to define one more term, which is having a lot of prominence in understanding the second law of thermodynamics or exergy analysis is irreversibility. The irreversibility is defined as the difference between maximum work and the actual work. So far, we have discussed what is its maximum potential or maximum capability for conversion, that I call it as maximum work or available energy. When it is coming to the practical conditions, we are getting the actual work. The difference between these two, we call it as irreversibility. Now the question arises, already I said that there must be some minimum quantity of heat energy that must be rejected. I am calling it as unavailable energy or energy. This energy and irreversibilities are same? Absolutely not. Engine. Even the reversible engine, energy will be there, that much quantity of heat that must be rejected. Over and above, whatever the loss that is occurring apart from this exergy, we call it as irreversibility, right? So the difference between maximum work and actual work, if you get practically the maximum work from that equipment, we do not bother much because the irreversibilities are zero. Whatever the maximum potential does it have has been transformed into actual work. Only problem lying is while transforming, if actual work is much less than your capable work, then the question arises. It is, we came to know from the exergy that it is having this much of capability, but when it is coming to the reality, we are not getting that much quantity of work. The difference between these two, we call it as irreversibility. In other words, the qualitative energy destroyed. Whatever the qualitative energy we feel before starting the analysis of a component or energy source or a system or a person or a cycle, it has its own maximum potential or maximum capability, but when it is coming to the reality, we are not getting that much. The difference means the qualitative energy we are foregoing. Where this qualitative energy is going? Theoretical ideal conditions, you are supposed to get your maximum work, but when it's coming to the practical conditions, you are not getting. These irreversibilities are because of this practicality. The irreversibilities are being incorporated into the system as well as the surroundings, so that the qualitative energy which you are supposed to expect from the system, we are foregoing. So we need to think more about irreversibility rather than exergy. Exergy, anyway, it is having the potential for conversion, but in that conversion, what is the loss that is occurring, we call it as irreversibility. It is our responsibility and it is our motto or it is our duty or analysis to be done to know the irreversibilities which are the equivalent to the loss of qualitative energy. It is being generally estimated based on entropy generation. So irreversibilities will come into the existence. Once the irreversibilities are existing means quantity of qualitative energy is being destroyed. Once the quantity of qualitative energy is being destroyed means automatically the entropy starts generating. Rather, in other words, entropy generation is being done in the system as well as surroundings which are creating the irreversibilities. The process are being made, reversible process as becoming irreversible because of this entropy generation. Once the entropy generation is existing, the irreversibilities are existing, the process becomes irreversible, the qualitative energy loss is occurring, which has to be protected by doing your so-called, it indicates lost work or loss in capacity of producing work when irreversibilities are present. Automatically, when irreversibilities are present, automatically you will be losing certain quantity of qualitative energy. Now we'll go to estimation of qualitative energy. I will give the loss of qualitative energy or irreversibility as per our definition, energy will have two components, exergy and energy. Out of exergy, we are losing certain quantity of energy, which we call it as irreversibility. That irreversibility, anyway, I don't want to discuss about these basic equations and relations which anybody can understand from the textbook, but the physical concept, the available energy or exergy for the flow process can be calculated based on enthalpy and entropy. Enthalpy, specific enthalpy and specific entropy will be the input parameters for the estimation of your W max or available energy or exergy or its capability. When it's coming to the W actual, that is your first law. When you say the first law of thermodynamics, the specific enthalpies difference will be equal to your actual work or W actual. Enthalpies are sufficient to make your first law analysis. For making second law analysis, enthalpy as well as entropy in combination you need to do. So W max for the open system or flow process and W actual, based on the difference between these two will come the irreversibility or loss of qualitative energy which is occurring, that is equal to T naught into delta S, S2 minus S1. That S2 minus S1, I can call it as delta S generation. If irreversibilities are zero, entropy generation is zero. Or if entropy generation is zero, maximum work output can be achieved. In a nutshell, this is a Gauss-Seidel equation which can be given as I is equal to T naught into delta S system plus surroundings. Only system cannot create any entropy generation. Entropy generation will be there in the system, and also the surrounding also play the role because of certain quantity of heat rejection to the surroundings unnecessarily. Slowly you are losing. So both the components, both entropy components will have the impact on irreversibilities. So energy will have exergy. Out of this exergy, irreversibilities which are losing unnecessarily while transformation, that irreversibilities are because of entropy generation. Anyway, T naught never be zero. If T naught is zero, it is a violation of second law or PMM2. So T naught never be zero. If entropy generation is zero, irreversibilities are zero. So entropy generation means disorder that is existing in the system, and the system has been affected by the surroundings. Similarly, for the non-flow process, it is being calculated based on internal energy. For trying to evaluate the process, it is based on. Finally, irreversibility for closed system also will be getting the same. Entropy generation, irreversibility is equal to the T naught into delta S. So entropy generation will have the lot of come to the entropy. Entropy is, we are able to know that entropy is having qualitative energy which is happening. Entropy generation is zero. Irreversibilities are zero. If entropy generation starts increasing,
Sir, just a minute, sir.
Yeah, please.
Sir, I request the participants kindly mute your mic. Mr. Santosh C. Thank you, thank you. Continue, sir.
My water for.
Yes, sir, yes, sir.
So entropy generation is the true parameter which is playing a vital role in incorporating the irreversibilities in the system and also the surroundings, so that the qualitative energy will be destroyed. Now entropy, as per its definition, it is a state property of the system like pressure, volume, temperature and so on. A quantity that changes as heat flows. As the heat is flowing from one location to other location or within the system from one location to other location, it is a measure of disorder. The disorderness which is existing in the system will be creating the disorderness that is existing in the system as well as surroundings will be creating this entropy generation. Once entropy generation is existing, which will be taking away our qualitative energy, which we supposed to get while transformation. Its units is joules per Kelvin, and the remaining things are known. If entropy generation is constant, sorry, if entropy generation is 0, that means entropy before process or after the process are same, then we can say that the process is a reversible process. Into entropy generation increases, the process is a reversible process. I would like to add one more point here. If entropy generation is negative, then it is practically impossible. The process cannot occur. You try to calculate the entropy generation for any of the system or any of the cycle or any of the process. Once if you get the entropy generation is negative, immediately we can say that the feasibility of the process cannot occur. The process cannot occur and it cannot be practically implemented. If the entropy generation is equal to 0, the process or a system, we can say that it is irreversible. As the entropy generation is increasing, the process becomes irreversible. Generally, I used to give an example by taking the students into account. As the student will come into the campus with a fresh mind, with so much of enthusiastic, whereas the surroundings are creating the disorderness to him. And some friends will come, let us go to the hotel, movie, and so on. The disorderness has been entered into the student life. Then he starts losing his enthu and his quality. Slowly, what will happen? He starts losing his marks. That means entropy generation is increasing because of the surrounding friends, and also in the campus, the teacher delivery and textbooks availability, question paper pattern, and all everything will put together will make the irreversibility. Though the student is having the capability to make these many marks based on his IQ level, but when it is coming to the results, by seeing the marks, he might have been failed as the disorder is increasing. So the disorder or entropy will have a lot of influence in the day-to-day life also. You have to question ourselves. Whenever the disorder is entering in our lifetime, immediately you have to say that we are going in the wrong direction. Immediately you have to change our direction. You have to minimize your entropy so that your quality of life will be improved and your exergy will be protected. In this way, entropy generation will play the vital role for the irreversibilities. Once the irreversibilities are existing in the system, immediately your quantity of qualitative energy is being lost or destroyed, or exergy is destroyed. Entropy maximized. When the entropy is maximized, once the heat rejection is maximum, conversion is 0. That means the case which has been shown here, in this case, complete heat rejection is existing 1000 kilojoules. You are unable to get even 0 work output from the system. It means the entropy is being maximized. Once the entropy is maximized, the quantity of qualitative energy has become 0. One should not reach to that level. So when do we say that the student's entropy generation is maximized? He gets 0 marks in the class. If after the exam 0 marks means his entropy is maximized and his irreversibilities are more and his capabilities are lost, and we can simply say that he is incapable to become the engineer until unless again he improves his quality by minimizing his own entropy. So whenever we do the second law analysis or exergy analysis, entropy will have the vital role. Entropy, by taking into the entropy and other thermodynamic properties, we will try to evaluate a composite property called exergy. Once the exergy is being calculated, based on the exergy, we will try to evaluate what will be the irreversibilities of the components. Irreversibilities are known, then you have to focus on the irreversibilities to minimize those irreversibilities so that the process parameters can be improved and performance or output can be better. So this briefly about irreversibility, entropy, and so on. Once after knowing the significance of exergy, energy, and irreversibility, entropy generation, all these are having the close relation. Energy will have certain component, that is exergy is the useful work, energy will be the useless work. In that exergy, again, irreversibilities are existing. Those irreversibilities are due to entropy generation. So based on entropy generation, we'll try to evaluate the irreversibilities. Based on the irreversibilities, we'll come to know that how much quantity of qualitative energy is destroyed in the system based on irreversibilities and entropy generation. So when you come to the second analysis or Exergy analysis. How to do the second analysis? Because the concepts are clear now. Exergy is known, irreversibilities are known, energy is known, how the surrounding is playing the role, that is also known. How the compound property or composite property based on enthalpy and entropy, how availability function can be calculated because based on the definition. I will show here. This one. So availability or availability function will be a composite property or Exergy, depends on the given condition. So whenever you want to do the Exergy analysis, energy analysis, which is already known, when it's coming to the Exergy analysis for any of the power cycle, either you take Kalina cycle, Bresson cycle, Otto cycle, diesel cycle, dual cycle, but any of the cycle, first you identify the components, identify the state points 1, 2, 3, 4 and so on. So those points will be considered as the entry point and exit point for each and every component. Those are being represented by thermodynamic coordinate system, which is well known to all of you. All the students who are mechanical engineering undergraduates, postgraduates and mechanical teachers, they know pretty well that how to draw this thermodynamic diagram on PV and TS diagrams and entry points and exit points. And each and every point will have its own thermodynamic properties. When it's coming to thermodynamic properties, we'll come to know that the pressure, volume, temperature, internal energy, enthalpy, entropy, Helmholtz function and Gibbs function. These are the 8 thermodynamic properties. If you know any of the 2, the remaining can be calculated based on the basics of thermodynamics. And we presume that before going to the analysis of any power cycle or any system, presume that we know the thermodynamic properties. What we need to do, we have to evaluate thermodynamic properties of specific enthalpy and specific entropy at all the state points. Enthalpy and entropy, these values, if I say the steam properties, steam tables are already available, depends on its condition, we can get those values directly. For gas, we know the relations based on the specific heats, you try to calculate those values. Or nowadays, ready-made subroutine programs are available for air properties, gas properties, steam properties, refrigerant properties and other things. Those values can be directly downloaded. Whenever you want to do the Exergy analysis, you must know the enthalpy and entropy. These 2 are the crucial parameters which are required at all the state points of the system. Once if you know the enthalpy and entropy, the procedure I will try to discuss here. The availability function has to be evaluated at each state point of the cycle based on enthalpy and entropy. As already I have mentioned, at each and every state point, you know the values of enthalpy and entropy. Once you know the enthalpy and entropy, you try to calculate the availability function for flow process H minus T naught S. Enthalpy minus T naught into S. You can see here. So H minus T naught S, we call it as availability function. H1 minus T naught S1 will be availability function at state point 1. H2 minus T naught S2 will be availability function at state 2. So whenever you try to follow do the Exergy analysis for a cycle or a system, you try to evaluate the availability function that has to be evaluated at each state point based on enthalpy and entropy. Once if you know the composite property, availability function at state points, the decrease in availability function would be calculated as available energy or maximum work or Exergy of the component. So whatever the difference between these 2 will be its maximum capability. So whenever you want to do the Exergy analysis means, first you try to calculate its maximum capability.
Participants, kindly wait for a while. There is a network issue on our resource person side. We'll be joining within few minutes.
Now I'm sharing my PPT.
Sir, your voice is audible. Yes, sir.
Yeah, I'm sharing my PPT. Yes.
Yes, sir. Yes, you can proceed, sir.
Yeah. So,
Thank you, sir.
are you audible now?
Yes, sir. Kindly proceed, sir.
Yeah. So what we'll do based on thermodynamic properties, we try to evaluate availability function at state points. The difference between these two, we call it as decrease in availability function. The difference we call it as its maximum work or W max. The actual work done by the component can be estimated as actual work. The difference between the enthalpy values H1 minus H2 for the state points of a system, we'll try to calculate W actual, right? So for each and every component, you need to calculate the availability function difference as W max and actual work as enthalpy difference. The next step, just a minute. The irreversibilities of the component can be calculated based on Gauss-Rodala equation that I have given T naught into delta S generation, which is equal to T naught into delta S system plus delta S surroundings. Already I have given that input. Based on that, also you can calculate irreversibility. Either W max minus W actual, that is one way of calculating the irreversibility. The Gauss-Rodala equation is another way. Either way you can calculate and you can compare. What would you know from here is, you'll come to know that what is the loss of qualitative energy is occurring in each and every component is known from the irreversibility, right? Exergy is one part, energy is another part, energy is another part, but crucial part is our irreversibility. If you know the irreversibility, loss of qualitative energy is occurring, and if you are able to minimize this irreversibility, definitely the system will work efficiently and the components will have the better efficiency. The total irreversibilities of entire cycle can be calculated as sum of all the individual irreversibilities. Each component, that is the beauty of second law analysis. When you come to the first law analysis, you will not be knowing network output by heat input, and you are trying to calculate the efficiency of a system, and we do not know where exactly the loss is occurring. Right? When it's coming to the second law analysis, each and every component has been thoroughly being verified by knowing its own irreversibilities. Each component will know that why the loss is occurring and what are the irreversibilities, and you try to work out to minimize those irreversibilities for the future design and output. The Exergy input of the cycle can be calculated based on the physical inputs. We calculate how much quantity of Exergy input into the cycle from the energy. Right? Once you know the energy input and irreversibilities, the second law efficiency can be calculated. The second law efficiency has been defined in many ways based on your exergetical output by exergetical input, and also by using Carnot efficiency. The different relations are available for calculating. To make you to understand the second law importance, if you say the first law thermodynamics, for steady flow process, when you say the steady flow, energy into the system is equivalent to energy leaving from the system. According to the first law, energy input minus energy output is equal to 0. You are not getting any information from any of the component based on the first law, but when it is coming to the second law, Exergy input, that means how much quantity of capable energy is flowing into the system, and Exergy output, what is the quantity of capable energy is coming out. The difference between these two will become irreversibility or Exergy destruction or qualitative energy destroyed. So which will give a lot of importance. In the first law, energy input minus energy output is equal to 0, whereas the second law is giving us Exergy input minus Exergy output is equal to irreversibility or Exergy destroyed. In this way, the second law efficiency has been calculated. Based on the second law efficiency performance, we will come to know that its significance and importance. Right? So with this, I wanted to give the inputs related to the energy, Exergy, how it is being quantified, and what is the role of dead state, and how the entropy is being made inputs to your reversible system into irreversible system, and so on. How to do the second law analysis has been given in detail for the participants. So just for understanding sake, I will discuss the class A statement so that the entire second law analysis has been completed. It is impossible to construct a device which operating in a cycle will produce no effect other than transfer of heat from a cooler body to a hotter body, or heat will not flow itself from lower temperature body to higher temperature body without any external energy source. That means energy will not flow itself. Energy will not flow itself from lower potential to higher potential. When you say the hot body to cold body, heat will flow on its own from higher temperature to lower temperature. But if you want to reverse that process, that means if you want to transform the heat from lower temperature to the higher temperature, you need to expedite some quantity of work, or the refrigerator has come into the existence based on the class A statement. So whenever the energy transfer is occurring between lower potential to higher potential, natural process is transformation of energy from higher potential to lower potential. If you want to reverse it, you need to expedite some quantity of work, so that then only it is possible from conversion of energy from lower potential to higher potential. So practically the refrigerator, if energy is existing at higher temperatures, and if you want to maintain that lower temperature below the surrounding temperature, you have to supply certain quantity of work. That means we are going against nature. Against nature, heat will flow on its own from higher temperature to lower temperature. If you want to make the heat to flow from lower temperature to the higher temperature, against the nature, immediately some quantity of work has to be expedited. Other example, suppose if you want to have the water at higher level, we have the higher potential. At lower level, it have the lower potential. If you just keep a pipe from higher level to the lower level, water will flow on its own, you will not do anything. If you want to transfer the water from lower level to higher level, definitely you have to keep a pump, so that it can be pumped. So we are going against nature. Whenever you want to go against nature, certainly you need to expedite some quantity of work. Similarly for the time also, yesterday is highly valuable than today, because if you could have done some work yesterday, is higher potential, today is the lower potential, the yesterday has become, that is the natural process. If I want to get back, if I want to reverse by applying the class A statement, which is absolutely impossible, so hence the time is highly valuable. The quality of time today is better than tomorrow. The quality of time is better yesterday than today, because you cannot reverse that. In other cases, for heat as well as water, you can reverse it by keeping refrigerator and pump. But for time, you cannot get apply this class A statement and you cannot reverse it. The time is highly valuable. Use the time effectively and do your duties comfortably and do better. So with this, I would like to conclude my session. If you have any questions, I am very much glad to answer for another 5 minutes left for us, because you have another section at 3:30. Any questions from the audience? I'm stopping sharing. So if you have any questions, I am very much answer for your questions. Shankar Ganesh?
Sir, still no questions from our chat session, sir.
Okay.
Seems there are no questions, sir.
Okay. If there are no questions, I am very much thankful to the organizers for giving me this opportunity to share the concepts which we got from our yeah.
Yeah, just a minute. Yes, participants, are there any questions to share with our expert? No, sir.
No.
No questions.
So if you don't have the questions, I am very much thankful to the coordinator and other my dear friends who called me for this lecture, and I am thankful to my dear friend Professor Sudipto De, who might be on the line or might be listening. And we too have learned all these things from our Guru Professor P.K. Nag. So we missed him and he is no more. Anyway, we will try to carry this information to all the students of mechanical engineering in the future course of time. Thank you very much for the given opportunity, and I wish you all the best.
Thank you, sir. Thank you, sir, for your delighted speech. Or continue.
Sudip today.
Hello, sir. Thank you, Kumar Sami, sir,
Thank
for
you.
enlightening us on the topic of the limitations of the first law of thermodynamics. It was very informational. I now request Mr. R. Vigneshwaran, Assistant Professor, Department of Mechanical Engineering, Kingston Engineering College, to give a brief introduction of keynote speaker G. Subramanian.
Good evening,